Good, how are you?
Good. Okay, this last week, last week, you indicated you were a little confused as to when you plug back into the original function, as opposed to the second derivative or the first derivative.
Yeah.
Well, I had a student pop this problem on me this week, and this is a perfect illustration as to when you do it.
Okay.
What we have here are two graphs. The top one is linear. It's y equal x plus 42. The bottom one is standard parabola, y equal x squared. Okay? The question becomes, their question is, what is the maximum length of vertical line that you can stick in there? It's not clear. In other words, we know this is 42 right there. That's the y-intercept of the linear line. So you could stick at least a 42-inch line right there. Clear that to the left of that y-axis, they're going to get smaller. To the right, we can't really tell whether they're going to get bigger or not. So this is a perfect calculus question. Any idea how we should proceed?
Not really, because I don't think we've gone to that stuff yet.
Well, you might have actually, but I'll help you and then you can tell me. What is the length of each of those vertical lines that I drew? What's the length of this one?
I don't know.
What's the y value here? That's y.
Yeah.
And this is y.
Okay.
So it's the straight line minus the parabola. In other words, if I take x plus 42 and subtract x squared, that's the straight line, that's the parabola, that blue line is the distance between them. An important concept to get, that the length of each of these blue lines that I drew is x plus 42 minus x squared. Okay, well, that becomes our new function. That's the length of a vertical line.
Okay.
Well, we're trying to maximize that length. So how do you maximize stuff in calculus? Take the first derivative, is almost always the first answer.
Yeah.
And set it equal to 0.
Yeah.
Okay. So if I take the first derivative, y prime, I get 1 minus 2x. If I set that equal to 0, I get x equal 1/2. So what that tells me is that right there at 1/2 is where the length of the blue line is going to be the longest. But the question was, what is the maximum length of the blue line? And what calculus allowed us to do was to solve for where on the x-axis that occurs. But we have to go back up into this function to figure out what the length of the blue line is. In other words, if I plug 1/2 in for x, I get 42 1/4. In other words, the length from here to there is 42 1/4, and nowhere else in that range is it longer. In other words, it gets shorter as you go this way. And so there's kind of a perfect application where you take the first derivative of your function, set it equal to 0,
Okay.
figure out where on the x x-axis, the maximum is going to occur, and then plug back that into the original function. In other words, the length of that line was x plus 42 minus x squared. So if I really want to know what the maximum length of the line is, I have to do this process here.
All right.
Okay?
Yeah.
I just wanted to show you that because it was such a perfect problem to illustrate where you plug back into the original function.
Yeah, thank you. That clears that up.
Okay, what have you been working on in class the last week? Where are you at?
So still just talking about on graphs where the values for x are like increasing and decreasing, and also just sketching a graph off of a given problem.
Okay. You got some problems that you can verbalize?
Yeah.
Okay.
So the first one we would have to graph f of x equals 2x cubed over x squared plus 1.
Okay.
And then for these, she gives us the derivative and second derivative. Do you want those two?
Yeah.
All right. The first derivative was 2x squared times x squared plus 3 over x squared plus 1 squared.
Yeah, I was going to say, we're going to have to apply the quotient rule, which means the math is going to be tough, or just lots of arithmetic, really. What's the second derivative?
Negative 4x times x squared minus 3 over x squared plus 1 cubed.
You would think it would be x squared plus 1 to the fourth, huh?
Yeah.
You know why it isn't? Is because when you applied the quotient rule to the first derivative, they must have ended up with an x squared plus 1 that they were able to factor out of the numerator. Because the bottom started out x squared plus 1 to the fourth. In other words, they got to square that to use the quotient rule, right? So the fact that it's now to the cubed means they must have done a lot of simplification. And for sure, if you start out with this function and you have to take the first derivative and the second derivative, it is a lot of college algebra. That's what it is. It's not so much calculus anymore, it's just a lot of college algebra. All right. And what do they want here?
So the domain is the first thing.
Of the original function?
Yes.
Okay. What is the domain of the original function?
Is it all real numbers?
Uh-huh. In other words, domain is what x could be. And if we look at this function, there's no value of x that's going to make the denominator 0, because that's always positive. Okay? So there's nothing that's restricting what x can be. So the domain is all reals. What else do they want?
Vertical asymptote.
Okay. None, for the same reason. What else?
Then holes.
The only way you get holes is if you can cancel something from the numerator and the denominator to simplify it. But that would involve dividing by, in other words, if I had something like x plus 1 times x minus 1, all divided by x plus 1. All right, let's divide it all by x minus 1. Okay? Now, right off the get-go, you might think, well, there's a vertical asymptote at 1, but there isn't, because that x minus 1 cancels with that to give me the x plus 1, but I have to carry forth that domain restriction. Just because I was able to divide top and bottom by x minus 1, still x cannot be equal to 1. That's how you get a hole.
Mm-hmm.
Well, there's nothing that I can divide top and bottom by to simplify your function. So there's no holes. At least not that I see. Now, are they asking these questions for all three or just the original function?
I think those are just for the original, and then use the other functions for the other stuff they're asking for you to sketch it.
Okay.
So the next ones are the x and y intercepts.
How do you get the x-intercepts?
Set y to 0, y is
Okay.
equal to 0.
So if I solve that, whenever you have a rational function equal to 0, what has to be true? Or, I mean, it's a good point to notice, because how are you going to solve that?
Could you just use the numerator? Or...
Exactly. In other words, that's what has to be true. The numerator has to be equal to 0. Okay? I don't have to specifically memorize that. In other words, if I attempted to solve this normally, I would multiply both sides by x squared plus 1. And then I would have 2x cubed equals 0.
Mm-hmm.
Okay? So you get to the same spot. But it saves you a little bit of time sometimes if you recognize, and there are some calculus problems that you kind of do have to recognize that if you have a rational function equal to 0, its numerator has to be 0. So what is the only x-intercept?
0.
And they want y-intercept also?
0 as well.
Well, what is x when you have the y-intercept? 0. So yeah, you start out by plugging in 0 for x and figure out what you get. And that's also 0. Okay. What other questions do they ask?
N behavior.
Which means what?
Where's the graph going when it's approaching negative infinity and infinity?
Correct. Not the graph, but where is f of x going?
Yeah.
Because when I do graph this, the vertical axis is going to be f of x. Okay? Well, when we're at negative infinity, what do we have? What's the numerator go to?
It goes to... I'm not sure.
Negative infinity. In other words, is all I'm going to do to investigate what happens is I'm going to let x equal negative infinity and see what happens to this thing. Well, the numerator goes to negative infinity. The denominator goes to positive infinity. There's one other thing you kind of have to know about end behavior. In other words, I can't figure it out from that. I don't know what negative infinity divided by positive infinity is equal to. Okay? It's kind of like 0 divided by 0. You're going to find in calculus that when you get to it next semester that there's things called indeterminates. And things like infinity divided by infinity, you don't know what it is right away.
Mm-hmm.
things like that. The thing that I do know for sure is that the numerator has a degree exactly one higher than the denominator. Okay? And whenever that's the case, you end up having an oblique asymptote. You remember oblique asymptotes from your pre-calc or not? Not
A little bit.
not everybody gets them, but in other words, we know what vertical asymptotes look like. We know what horizontal asymptotes look like. Oblique asymptotes you get whenever this is exactly one power higher than the denominator. And then you divide this into that to get the equation of that asymptote. Well, the equation of that asymptote is going to be 2x. Okay? So that asymptote that's going to control this, we don't have any vertical asymptotes. We are going to have just this asymptote. Let me draw it properly. It's going to be, I'm going to have to go downward to draw this thing right. But in other words, the function is going to have an oblique asymptote, and it's also going to have a horizontal asymptote. The horizontal asymptote is 0. Y equals 0. And you know that by, if I do this long division, I don't want to get bogged down in this, but it's useful for the moment. First thing you get is 2x. Hold on. And then when you multiply back, you get 2x cubed plus 2x. And there's an imaginary 0x. You end up with a remainder. And the remainder is divided by x squared plus 1. In other words, whatever remainder you end up with, it's always divided by that, and it's going to have a horizontal asymptote at 0. In other words, let me just give you a couple of situations to refresh you here. If I have this, that's a horizontal asymptote at 0. Because the highest degree in the numerator is less than the highest degree in the denominator. That's always y equals 0. If they are the same, let's make it 4x cubed. Now the highest degree is the same. Now we have a horizontal asymptote at y equal 4, whatever the ratio of the coefficients is. Okay? And the third case is the case we're looking at here, where you have the numerator has the higher power. Ooh, yeah, no, that's correct. And the way you figure out your asymptotes here is to do the long division, and whatever that comes out to be is the equation of your oblique asymptote. But there's always a remainder, and the remainder is going to be x, some number of x over x squared plus 1. That has a horizontal asymptote of y equals 0 always. Okay? So whenever you have an oblique asymptote like this, you always have a horizontal asymptote also. Now, what we typically are looking at in the way of graphs, in other words, this original graph is hyperbolic. And when you draw your asymptotes and you have a grid of asymptotes like this, Well, the function is going to approach your asymptotes like a typical hyperbolic function does. It's not always in the first and third quadrant. Sometimes it's in the second and fourth, and it's easy enough to check. Notice that as x went to negative infinity, we can now see what y is going to. 0 from the graph.
Okay.
In other words, that's headed to the horizontal asymptote of 0. And you, in fact, end up with horizontal asymptotes that mean in behavior. In other words, the way you get a horizontal asymptote is that's what the function does as you go to negative infinity. And what does the function do as you go to positive infinity? Well, it goes to 0 also. So 0 is the end behavior for both directions. What else did they want to know?
Relative extrema.
Okay. How are we going to find those?
With the derivative.
Okay. Where are the relative extrema going to exist?
You set it less than or greater than 0.
It's where your first derivative is going to be equal to 0
Okay.
or undefined.
Mhm.
Because if it's undefined, that's potential. In other words, if I have a function like this, well, that's a relative extrema, but the first derivative is undefined there. So I can't take the first derivative of this absolute value function here and set it equal to 0. This point won't show up. But if I check where it might be undefined, it will. Well, let's see. If we look at our first derivative function, it's not undefined anywhere, because this can only be a positive number. There is no value of x that makes the denominator 0, so it's undefined nowhere, but where is it equal to 0?
The numerator is equal to 0. So
What makes the numerator equal to 0?
Hold on, let me do this real quick. Is it the root of -3?
Well, that's a imaginary number, so we want to stay in the non-complex plane. The only thing that makes this thing equal to 0 is if x is 0. There is no value for this that'll make it -3.
Okay.
Okay, so only 0. So Extrema x equals 0. Now, if you look at the graph that I have drawn, you can see that there is no point on that thing where it's flat tangent. There's just, if I look at this part of it here, there is no point. This is not a flat tangent. That's going to be always decreasing. It's increasing from here up to there, but there's no point that I can find a flat tangent. So my curve is not right. not if the first derivative is telling us that there has to be an extrema at x equals 0. And in fact, I've got an x-intercept of 0 also, and a y-intercept of 0. So this picture can't be right. What else do they want besides extrema?
Just a point of a POI.
POI meaning point of inflection?
Yeah.
Where do you get points of inflection?
Second derivative.
What makes the second derivative equal to 0?
Well, 0, right?
Well, that's 1. Where else? Because in this one, this can be 0. In other words, unless I wrote this down wrong, was the first derivative x squared plus 3 and the second derivative was x squared minus 3?
Yeah, that's right.
Okay, so square root of 3 plus or minus the square root of 3. So we have 3 points of inflection. Still trying to figure out how we have anything at all at x equals 0, but we should. Yeah, I'm doing something wrong with my approximate graph here. Let's get rid of that. We definitely have a... Oh, I know what I did. I didn't draw my horizontal asymptote properly. It didn't go through the origin. Let's just do the math here. This isn't that easy to actually divide out. This was 2x cubed. Well, if I put in all my dummy variables, which you kind of have to do, and I kind of have to do it in both cases. Wow. Yeah, that's a hard one to do. In other words, that gives me 2x cubed plus 2x. Maybe I don't need that dummy variable there. I do need it here, though, because that's going to give me minus 2x. And then I divide that, and so my answer is remainder of minus 2x divided by x squared plus 1. That should be an asymptote, horizontal asymptote at x equals 0, which is what I had in my picture. So, I start with that vertical asymptote, or rather the oblique asymptote, and the horizontal asymptote. My function does go through. Now you are allowed to cross horizontal and oblique asymptotes, incidentally. They're not like vertical asymptotes. Vertical asymptotes can never be crossed because the value at x can never be causing division by 0. But horizontal asymptotes can be crossed. So we could have a function that crosses both the horizontal and the oblique asymptote here. We clearly have a point on the function right there because we know we have an x-intercept and a y-intercept. And we know the end behavior.
So
this thing is going to look, and we also know that there is a horizontal tangent line at x equals 0. So how could we graph this thing? Let me think. the first derivative is always positive, right? If I look at the first derivative, it's always positive. There's no value for x that causes either the numerator or the denominator to ever be negative. So it's always increasing, this function is. What do always increasing functions look like? How in the heck do we get an extrema at x equals 0? I don't want to take up too much time trying to figure this out. Let me bring up Wolfram Alpha, we'll graph it, and we'll answer most of our questions. This was 2x cubed divided by x squared plus 1, divided by the quantity x squared plus 1. Okay. I see. Notice how the function is going towards a horizontal oblique asymptote. In other words, if you draw that oblique asymptote, y equal 2x through there, you'll see that this function, and in fact, if you scale out, you can tell that it is headed towards that oblique asymptote as x goes to infinity.
Okay.
Which is infinite. I was wrong. There does not appear to be a horizontal asymptote here. I'm not quite sure why, but let's go back and talk about the end behavior. The end behavior is going to be controlled by whatever asymptote you have, and this appears to only have an oblique asymptote. So if I say, what does this function do as we go to negative infinity, well, what does it do?
F of x approaches negative infinity.
And if I go to positive infinity?
F of x goes to infinity.
Okay. So that's our end behavior. How we were supposed to determine that, I guess, had to do with that horizontal or that oblique asymptote. Yeah. If I hadn't put the horizontal asymptote in there, that's what I would have said. Still not totally sure why we don't have a horizontal asymptote, but everything else about this makes sense. Notice that we appear to have an extrema right there, right?
Yeah, okay, yep.
But we don't. It's not an extrema. It's just a horizontal tangent line. In other words, sometimes horizontal tangent lines are not extrema. If I take the function y equal x cubed, looks like this. We have a flat tangent line at x equals 0, but there's no extrema. That's not an extrema. In order for it to be an extrema, it has to actually pass the first derivative test, which says the slope have to change on either side of it. Well, notice in the case I've drawn here, it goes plus, 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 0, plus, plus, plus. My slopes don't change. For it to be a maximum, they would have to go from plus to minus, and for it to be a minimum, they would have to go from minus to plus. In other words, if I have a maximum, I'm going plus, 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 0, minus, minus, minus. If I have a minimum, it goes the other way. Minus, 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 0, plus, plus, plus. So just because a first derivative is equal to 0 doesn't mean there's an extrema there. It just means it's a possible site for an extrema. You kind of have to test that point. In other words, when we got our extrema at x equals 0, we need to go back to the first derivative and test what happens on either side of 0. Well, clearly the slopes aren't going to change. They're not going to go from positive to negative because this thing is always positive. So it's going to go from positive to positive as we go on either side of 0. So that didn't pass the first derivative test, so it failed the first derivative test. It's not an extrema. Okay? There's also a second derivative test, which tells you about concavity, but in this case, the second derivative test is negative, which tells you it's always concave up at that point. I think, let's see, when we plug in 0 into the second derivative, yeah, we get a negative 3 up. Oh, no, we don't. We get a 0 up top, and we get a positive, so it's 0. So when the second derivative test is 0, it doesn't tell you much about the extrema. In other words, I know this gets really complicated, and it's hard to understand, and I'm probably confusing the hell out of you, but you check your first derivative to see where it's 0 or undefined, and we did that. We found one spot that it was 0. Well, if we want to know if that's really an extrema, we'll check the second derivative. Well, if I check the second derivative and evaluate it for x equals 0, I get 0. So the second derivative does not give me any additional information about what kind of extrema we might have found at x equals 0. The only test left to determine if that's a minimum or a maximum is the first derivative test. So you go on either side of 0 and find out if your first derivative changed signs. And since this thing is always positive, it's not going to change signs. It's going to go plus, 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 0, plus, plus, plus. So it fails the first derivative test. That's not an extrema. Now, the inflection points that we came up with. If I pull the curve up here, notice that we do have concave down on this part of the graph, and we have concave up on this part of the graph. Well, the inflection point is always the exact point where that concavity changes from down to up. And we can see that it's only at x equals 0. These other two inflection points don't appear to be inflection points. I suppose it's possible that this graph might just be, in other words, what did it say? It said square root of 3, which is 1.7. So is there an inflection point right there? Second derivative is 0 at square root of 3 plus and minus. What that could be telling us is this graph comes back and turns back to concave up. Right about here. And right about here. In other words, this graph, or concave down on this side and concave up on this side, to give us an inflection point at square root of 3 plus or minus square root of 3. Let's see if Wolfram alpha gives us any more additional information. They give you the first derivative. They don't give you the inflection points or the second derivative.
So I pulled up what she did for that problem. She has it concave up until negative root 3.
Okay.
Then concave down until 0.
Okay.
Concave up until positive root 3, and then down as it approaches infinity.
Yeah, that makes more sense than, here, let me draw what she said and why it looks different than Wolfram alpha. In other words, this looks pretty smooth. This you would assume it's concave down all the way to negative infinity, but it's not, apparently. It looks more like this. And then at square root of 3, turns around and it becomes more like that. And at negative square root of 3, it turns around and becomes like that. So if we were able to zoom in on this in the Wolfram alpha, I would see that concavity changing. And I can't see it on this either. I'm not looking at it at a close enough scale, and this doesn't give me the ability to zoom in on it. But because of the first derivative and second derivative, it basically, we know the curve has to look something like this. In other words, there must be an inflection point right there. There's an inflection point right there. And there's an inflection point right there. This was a tough problem. This was a really tough problem. And we've got this oblique asymptote that this function is approaching as we go to the infinities on both sides. So this function clearly is going to cross this asymptote, but it's going to stick to it like glue. Interesting. Okay. Well, what else you got? Is there anything else about that problem that we didn't cover? I mean, I messed it up a little, quite a bit, but the end behavior is negative infinity, or negative infinity and positive infinity. We determined that was not an extrema. And we got our 3 inflection points. I just didn't translate that to the proper looking graph, but I should have. I understand exactly now why she came up with something that looked like this.
Yeah, I think for that problem, that's it.
Okay, what else you got?
You want just another graphing one, if that's okay?
Yeah. Yeah, we got about, is it, well, we should be able to do it in 15 minutes.
Yeah, because that's really all we've done this week, because
Okay.
all next week's fall break. So,
Okay.
so we have,
Incidentally, before I get it, can I get your mom's email address real quick?
yeah,
That's the only way I have to on-voice her. What is it?
KJ Myers
Okay.
4.
Was the number 4?
Yeah,
Okay.
at gmail.com.
Okay. Here, let me just make sure I spelled it properly. You said KJ Myers 4 at Gmail. Like that? No E.
Yeah.
Just MYERS. Okay, cool.
Mm-hmm.
Go? Yeah, okay. What do you got as another problem? If I can do this one without botching it.
So f of x equals 3x minus 2 over x squared minus 2x plus 1.
Notice what that is. That's also x minus 1 squared, which might be more useful to put it in like that. What first derivative?
Yeah. Negative 3x plus 1 over x minus 1 cubed.
And the second derivative.
6x over x minus 1 to the fourth.
Okay. The domain. Is all reals except what?
1.
All reals except x cannot be 1. Vertical asymptote. It's whatever makes the denominator 0.
So 1 again.
Only x equal 1 is a vertical asymptote. What was the next thing they wanted? Holes? I don't see any. There's nothing I can take out of the top and the bottom. So I've got none. What did they want after holes? End behavior?
The x and y-intercepts.
X-intercept is when y equals 0. What is that going to be?
Let's see, 2/3.
I think it's negative 2/3.
Negative 2/3.
Yeah, when x is negative 2/3, that makes the numerator 0. Oh, no, positive, excuse me. Positive is correct. Y-intercept.
Let's see, 0. Is it either 0 or like undefined or not?
Well, just plug in x or 0 for x. In other words, the y-intercept means x is 0. So if I plug in 0 for x here, I get minus 2 over positive 1.
So negative 2.
Okay.
Fine.
End behavior. This one's a little easier than the other one because here our bottom is bigger than the top. In other words, if I expand that out, I've got an x squared. Well, I only have an x in the numerator. So I immediately know that I have a horizontal asymptote at y equals 0. And that dictates my end behavior. So what is my end behavior going to be? If I have a horizontal asymptote at y equals 0, which I do, then my end behavior has to be 0. Has to go to 0 at negative infinity, and it has to go to 0 at positive infinity. Based on that horizontal asymptote. Okay?
Okay.
And what next?
Relative max and min.
Extrema. Okay. So let's see. If we look at the first derivative, let's talk about extrema. Where is the first derivative equal to 0 or undefined? Where is it equal to 0?
Is it undefined at 1?
It's undefined at 1. So, where is it equal to 0? It's where the numerator is equal to 0. And we're talking about the first derivative here. So where's the numerator? Negative 1/3? No, positive 1/3. In other words, when x is positive 1/3, we got minus 1 plus 1. Okay, so it's x equal 1/3 and 1 is where it's undefined. So those are the points we have to examine to figure out relative extrema. Now, we can actually use the second derivative to do that. Okay, let's plug in x equal 1/3 into the second derivative. What do you get? Is it positive or negative?
Is positive?
Correct. What does that mean about the concavity of the function? Positive goes with what kind of concavity?
It's concave up.
Yes. Just remember, positive goes with up, negative goes with down. Concave up means what kind of an extrema are we looking at?
Min.
Yes. So we have a min at 1/3. Now, the first derivative and the second derivative are both undefined at 1. So we don't have a min at 1. In fact, we know we have a vertical asymptote there. So we can't have a minimum or a maximum there. Okay, so we kind of know that just based on the fact you have a vertical asymptote. Remember, when you have a vertical asymptote, the function cannot cross it. So the only thing it can do is approach negative or positive infinity. That's not an extrema. Infinity is never the extrema. Okay?
Okay.
Has to be a precise number for it to be one. Okay, and points of inflection, was that the last thing?
Yeah.
Points of inflection is where the second derivative is equal to 0. Well, that's at x equals 0. And only there. So, how can we draw this curve? Let's see. What's going to fit all of these cases? Well, clearly when x is negative, look at this denominator on the second derivative. That's always positive. Anytime you have something being taken to the fourth power, it's positive, except it's undefined at 1. But any other value for x, and the denominator is positive. Okay? So when x is negative, the second derivative is negative. Concave down. So if I were to go to draw my chart, just loosely here, what do we know? We know that, here, let's put the points in. X-intercept at 2/3. Y-intercept at -2. So we know we go through those 2 points. We have a vertical asymptote at x equal 1. We have a horizontal asymptote at y equal 1. This function is definitely hyperbolic in nature. And let's see, what else do we know about it? No holes. I got my intercepts on there. I know my end behavior is going to go towards this horizontal asymptote in both directions. I have an extrema at x equal 1/3. That's an extrema. Well, what would give me an extrema there? Let's see, for it to go through this y-intercept and that point, I'm trying to imagine what this thing might look like. Something like and on this side, perhaps like this. In other words, very hyperbolic in nature. Now let's see if that passes all of our tests. We're supposed to have an extrema here. Not the way I drew it. Let's draw this way. Now, or kind of like this. Okay, now we can see that we would have an extrema right there. And the other side of that would have to be something like this. Let's see, so that gives us an extrema at 1/3. It doesn't go through this Y-intercept the way I drew it. You can kind of see what I'm doing though, right?
Mm-hmm. Yeah.
Trying to figure out how I can put a hyperbolic looking function in there, doesn't cross this vertical asymptote, goes through those 2 points, and has a 0 thing right there at x equal 1/3. Well, to save time, let's graph this one. 3x minus 2 over x minus 1 squared. Quantity 3x minus 2 divided by the quantity x minus 1 squared. That's how it's graphed. Yeah, that fits everything, doesn't it? In other words, notice there's the vertical asymptote. There at 1/3 we can see we have a flat tangent line, and then it curls back and heads towards the horizontal asymptote. So we got everything right except I couldn't draw the curve right. I was trying to draw it in opposite frames, most hyperbolic functions, but not this one. This hyperbolic function, I was off. It was real easy to draw it. I just didn't see it. It was like this. And then the other side, like that. Yeah, I don't know why I couldn't see that. I guess when you got to always be a little bit leery if you're drawing hyperbolic functions. Most of the time, they're going to look like this. Or occasionally, they'll be in the second and fourth quadrant, like this. But sometimes, like 1 over x squared, they're in the first and second quadrant, like this. And this kind of function looked approximately like that, but it had to go through the x-axis and the y-intercept at the right spots. All right. So, are we not going to have a session next Friday?
Well, I'm gonna be in Durango next Friday.
Okay. So I'll cancel next Friday's session, and we'll meet 2 weeks from today. Does that work?
Yeah, that works.
Okay. Let me just do it while I'm thinking. Next Friday is the 16th. And cancel that one only. Okay, cool. Well, enjoy your holiday.
Yeah, thank you.
Going to Durango, huh? Yes.
Yeah, we're visiting Fort Lewis.
Oh, visiting. You're thinking about going to Fort Lewis?
Yeah, I want to try to play soccer there.
Oh, I was going to say, we used to play them in football. That was they're in the same conference as mines, or at least they used to be.
Yeah.
So, all right, Jackson, I will talk to you in 2 weeks.
All right. Yeah, see ya.
Bye-bye.